theory prediction, ferromagnet is crucial. One of the issues.
Yes, at low temperatures, it's usually only one mode which is occupied. In that case, you do not have to worry about the ferromagnetic nature. But if you go to room temperature, you will know that many spin waves are occupied. And then simple single band magnon model does not work. That is
I just wonder, Professor Saito mentioned that when you use magnetite, which is also very good ferromagnet, and this spin secret coefficient increased by 400-fold, something like that.
That was yeah, that's a good remark. But this increase was seen only in multi-layers, not at the single interface.
Okay.
So the effect Professor Saito was mentioning is an enhancement of the effect if you grow a multi-layer. And it's very difficult to grow a multi-layer with gig. It's easier to use magnetite.
Yeah.
The disadvantage is that magnetite is not really an insulator.
Yeah, it's half metal or something.
Yes, at room temperature, it's a bad metal.
Yeah.
So why it is poor metal.
Okay.
I understand. You say that a heat, a heat wave, or when you locally heat your sample, is equivalent to a shear.
No, I think it's said what you're doing is you are heating the sample, and it will generate both pressure waves and shear waves.
Okay.
And so it's difficult to calculate the ratio, but you see, what you can do is you can simply fit theory to experiment, because here we have both, right? So both shear and pressure waves, and here you see the experiment, and you can sort of see from these comparisons. This one here is generated by a shear wave. There's a completely different symmetry, see? And then this one. This one has a four-fold symmetry, this has two-fold.
So this is basically because you excite phonons and they are both longitudinal and transverse, right?
Yes.
That's the idea.
Yes, you're exciting both, and one is slower than the other, so that they get nicely separated.
They get separated.
Yes. And I think if you do proper calculations, you can sort of reconstruct what the laser exactly has been doing to create the initial conditions for this.
Yes, in your new interesting crystal, GIG, in your very interesting crystal, GIG, GIG.
Yes.
I wonder, for other rare elements,
yes,
is it possible to replace gadolinium with fluorine, erbium, dysprosium?
Yes.
Something even more interesting may happen?
Yes, that is quite possible.
You haven't done it, or theoretically?
That's a secret. That is all secret yet.
Until next time.
Yeah.
I found the spin difference in the ink in the exist lecture very a lot. What's your suggestion on that? The spin difference of ink. Spin difference. Spin diffusion in ink very a lot in the exist lecture. What is your suggestion?
Okay, right. So what I've discussed is mainly the physics exactly at the interface. You are right, I skipped this completely, but if you really want to quantitatively model this conservative effect, you have to use this as a boundary conditions for the spin diffusion equation on the normal magnet side, and the spin diffusion also on the ferromagnetic side. Right? That's what you do. On the metal side, we know, or of course there's lots of discussions, what is the spin diffusion in platinum, for example. Is this 1 nanometer or is it 10 nanometer? But we have similar discussion on the ferromagnetic side, indeed, on the diffusion length of the magnets. There you have to distinguish the elastic diffusion length and you have to inelastic diffusion length. Actually, there are no reliable data available yet, but many experiments are going on to find out what this number is. So Magnetic field dependence, for example, is one way you can do that. And you also need some modeling. So that is also work going on, and I cannot show any definite results in this direction. But indeed, the Magnon diffusion length, the Magnon spin, the Magnon relaxation length is a very important parameter. But it turns out that it looks like this parameter can be really very long also at room temperature. And I would like to refer to experiments by the Groningen group and also Ohio State University, which are sort of finding this result.
Any further questions? I have a yeah,
Oh, no, but it was something, no.
you show that in gig or YIG, this spin zeta quite high at the room temperature. That's because one of the maximum mode going down.
Yes.
Yeah, and you say that the key is that the maximum is chiral.
Yes.
Yeah, but usually you have should be doubly degenerate, isn't it? One left hand and the other right hand. But when this one is a single.
So that is this degenerated mode you have when you are working with antiferromagnets. In antiferromagnets, these two are degenerate.
Yeah.
And indeed, I think people agree now that there should be no spin-Seebeck effect for antiferromagnets, unless you apply large magnetic field and make a spin-flop transition. But these two degenerate modes, they indeed pump spin currents into the normal metal with opposite sign, and the total result is zero. If you make a ferrimagnet out of this antiferromagnet, you're just splitting these two.
Okay.
Right? And as soon you have a split, you make it a ferrimagnet.
I see.
So the ferrimagnet sort of breaks this degeneracy between the two chiral modes. And that's of course because of this ferromagnet time reversal symmetry is really broken.
So this breaking needed to be larger than room temperature. I mean the degeneracy.
Yes.
Okay, if there's no further questions, let's thank you, Professor Bauer again.
Thank you very much.
Now, let's move on to the last talk in this morning. The speaker is Gerrit. He's a young, bright scientist in the field. He's working. I just moved back to China in Beijing Normal University from, I guess, mainly from Netherlands. Okay, but stay a few days in Mainz. Yeah. Okay. And so today he's going to tell us about the role of interface in spin transport inside gain from first principle calculation. Welcome, Professor Yeo.
Thank you, Wang, for a nice introduction. And it's very nice for me, the first time visiting Taiwan, and especially Tsinghua University. Actually, I was studying in the other Tsinghua University long time ago. And today I'm going to talk about mainly the spintronics, what happened at the interfaces. There are a lot of phenomena that has been overlooked by the spintronics community and give rise to a severe consequence. For instance, there are a lot of debates on important parameters like spin fleet diffusion length of platinum. Our previous speaker mentioned it's 1 nanometer or 10 nanometers, and also spin Hall angle, for instance, of platinum. I should first mention my collaborators from Beijing and also from Twente. Two important persons. She implemented all the finite temperature schemes that allow us to go beyond zero temperature. We know first principle studies usually works only at the zero temperature. But as we discussed before the excursion day, Giovanni and Saito-san and Gerrit, if one of the most attractions of the spintronics is that it works at room temperature. So if we cannot really study the final temperature effects, that we would miss a lot of real things. So this is an important thing we do, and also she implemented a realistic modeling of interface with large lattice mismatch, how we get rid of the string effect in the modeling. And most importantly, she's my wife. She also contributes a lot more than that. And another person, Ring Wessling, he's a musician. He composed, he played trombone in orchestras, and also he developed computer programs. So he implemented this local current scheme that allows us to study the spin Hall effect and anomalous Hall effect in real materials. So as we said, as we know, we should go to final temperature, at least the room temperature. We want to study it in a way that we can see the intuitive picture, transparent picture, and also without tunable parameters that makes our study reliable. So taking platinum, FCC platinum as an example, how we do final temperature effects, we can calculate the phonon. We know how the atoms vibrate at room temperature. This is almost a standard way to do it within density functional perturbation theory, and we see the calculated phonon spectrum has a reasonable agreement with experiments. And after having the spectrum, we can populate phonon using Bose-Einstein distribution. It's what we learned in solid-state physics. And after populate phonon, we are able to get some snapshots. We just take one time, a fixed time, and get a snapshot of disordered platinum, like this. They are moved away from equilibrium positions, and then we connect this snapshot to electrodes and perform a transport calculation to study it. And we know the connection electrons are much faster than the atomic vibrations. So this is the Bohr-Oppenheimer approximation, and it gives a reasonable physical picture. And we can also tune the length scale, the length of the disordered region. And according to Ohm's law, we should get a linear dependence. And this is what we get. And different points here shows different random configurations by populating phonons or taking different snapshots. And from the slope of this line, we get the room temperature resistivity of platinum, box platinum, is about 10 microohm centimeter. And compared to well-documented data in experiments, it's 10.8. So in this calculation, we do not introduce any tunable parameters. That is, everything is automatically out from the calculation. And as a task, we calculated temperature-dependent resistivity of copper, palladium, platinum. Overall, we get a very good agreement with experimental data. And here, for copper, there's no effect if we turn on spin coupling or turn off it, because copper has very weak spin coupling, and also at the Fermi level, it's dominated by s electrons. So it has very little effect. If we do spin coupling, we couldn't see any difference from this figure. But for palladium and platinum, the spin coupling has very large effect, noticeable effects. Why is that? Because it's just normal matter spin degenerates. So spin coupling affects the resistivity in two ways. First is it lifts the band degeneracy around the Fermi level. So the Fermi surface will be changed a little bit by the spin coupling. For instance, this is the band structure of platinum. At the Fermi level, I don't know if you can really distinguish the colors. Well, the dots are without spin coupling and the line, solid lines with spin coupling. And you do see a little bit difference. But this splitting is not large enough to account for this almost 30% difference in platinum. And the most important reason is that spin optic coupling allows spin flip scattering by photons that increase the phase space of final states of the photon scattering. That is very important. And here we see even for normal metal, non-magnetic metal, spin coupling is very important if we want to study the transport property. So this is just a numerical check to demonstrate our final temperature scheme works well. So we are more interested in the spin manipulation. We know spin coupling also dissipates angular momentum. So if we inject a pure spin current from the left lead, then because of the spin flip scattering, it will gradually lose its spin polarization. At a certain distance far away from the interface, it will go back to equilibrium because this platinum, non-magnetic metal, it should be the polarization should be 0. And this length scale is so-called spin flip diffusion length. Our previous speakers all mentioned this, and also Giovanni has some opinion about this for platinum. And if you really want to know the bulk value, this is the bulk value, 5.5 nanometers at room temperature. And keep this in mind because I'm going to confirm it later by another independent scheme, commutation scheme. Okay, so this is what we get from the calculation. And also we started the temperature dependence of the spin diffusion length of platinum platinum. As we increase the temperature, the scattering becomes stronger and stronger, and then spin diffusion length decrease a little bit as a function of temperature. We have plotted a function of conductivity. Then we see the linear dependence. And this linear dependence is actually confirmed that the main mechanism of the spin relaxation in palladium is Elliott effect. Because in Elliott effect picture, the spin flip time is proportional to this momentum relaxation time. So, and also we compare with the experimental data. For most of the data I showed here, they are reasonable, but there are some points deviate from this linear dependence. And this figure is completely misleading because you don't see large difference. But if you blow up here, you see they are completely different size, about 5 or 10 nanometers, and these are 1 nanometer, about 1 nanometers. So then we examine all these data extracted from the experiments. And we noticed that most of these data are extracted from spin pumping and inverse spin Hall effects, this kind of experiments. Then let me give some background. So by performing FMR measurements, and we can measure the Gerrit damping. And the Gerrit damping is, it's a kind of the dissipation in magnetization dynamics. And we know if we have magnetic moment in effective field, it will precess, right? But this precession does not dissipate energy. And what in reality, when it precesses, it also approach the direction of effective field and eventually align with this field by dissipating the angular momentum and energy. This damping mechanism is described by this Gerrit damping term, and the alpha is called Gerrit damping parameter. And in 2001, a Japanese group discovered that if you have a ferromagnetic material like permalloy sandwiched by a normal metal like platinum or palladium, then you will find the damping parameter is enhanced by this normal metal and is inversely proportional to the thickness of this permalloy ferromagnetic layer. And this soon was explained by our previous speaker, Gerrit, and his collaborators using a spin pumping picture. That is when the magnetization process is pump spin current into the normal metal, and then by spin flip diffusion lens, spin flip scattering, the spin current dissipates in the normal metal and give you extra dissipation. This is called interface enhanced Gerrit damping, and this is all well understood qualitatively, but not quantitatively. So the quantitative reproduce of this data was not successful until last year. We performed first principle calculations, and we get all this 1/d dependence and also the material dependence of these normal metals. Since we are able to quantitatively study the interface enhanced damping, we try to understand what happened in the extracting this spin flip diffusion lens. So we try to simulate the experiment, mimic the experiment by calculating the Gerrit damping parameter as a function of normal metal thickness here. And we get for 1 nanometer permalloy or 2 nanometer permalloy, we get two series of data. And the key point, this is exactly what is seen in experiments. But the key issue is how to interpret, how to model this data from experiment or from our calculation. And let's look at the system. So in literature, we only assume that the dissipation happened in the bulk normal metal. So that is characterized by the spin flip diffusion lens of the bulk material, LSF. But there's another mechanism. At the interface, when the spin current goes through, it will dissipate because there's a small coupling, there's the interface scattering, so it must be something lost at the interface. But nobody really take it into account. Now we can do a test. If we completely neglect the interface spin current loss, we can fit the spin diffusion lens. It's very short, of course, because you attribute all the loss into the bulk spin diffusion lens. You end up with a very short LSF. But this is wrong. Why is it wrong? Because we have already demonstrated in a very transparent calculation that spin diffusion lens is by 5 by 5. So why the discrepancy is actually indeed the neglect of the interface effect. So if we take that into account, then we get a much better fit to the calculated data, and we realize the interface spin memory loss is very large. So more than 90% spin current flip at the interface. So actually, there isn't much loss in bulk platinum. And indeed, we also checked the platinum has very little spin accumulation in platinum. So that also is an evidence that most of the spin current already lost at the interface. So then we kind of understand this discrepancy, the debate of the value of spin flip diffusion lens in literature in these years arise from actually the improper neglect of the interface mechanism. So this is an example of by performing very careful and reliable first principle calculations, we can really identify some important process that has been overlooked by the community. And in the next example, I will show that the interface also can generate spin currents. It's a very, also give a significant contribution. We have heard from Saito-san's talk about spin Hall effect and inverse spin Hall effect. They are reciprocal processes, and the efficiency of converting spin Hall effect, charge current to spin current, or spin current to charge current, is characterized by this dimensionless parameter, material parameter, spin Hall angle. And also, the experimental reported spin Hall angle for platinum spread from, for instance, 0.3% to 12%, 11%. So it's no consensus for this value. And this is actually very new data. It's reviewed by Cairo this year. And if we look at how in experiments we extract the spin Hall angle, this is the one typical setup, the spin pumping plus inverse spin Hall effect invented by Saito-san. And we see the spin current is pumped by oscillating magnetization through an interface into platinum. So that's the interface. And also, another technique, like spin Hall effect plus spin transfer torque, we drive a current in platinum or this tantalum, and then using spin Hall effect generate spin current, and drive this spin current into the ferromagnet in contact and switch the ferromagnet. And here, there's also an interface. So in almost all the experimental setups, there's an interface involved. But in all the theoretical models, they are completely neglected. And and these models were used to extract spin Hall angle. So this, of course, will cause some problem. Now, we have to do it carefully. How can we study this spin Hall effect or inverse spin Hall? Okay, I forgot to mention. There's actually an evidence also by Saito-san's group and collaborators. They indeed see the different contribution in spin Hall effect. For instance, this is bismuth. The spin Hall angle for bismuth they found is positive, but the interface between bismuth and permalloy is opposite. The spin Hall angle is opposite. So there's evidence that it shouldn't be the same. So the interface can be very important, give you a very large effect. And if we want to do it, we first develop this local curve scheme. This scheme is out of the literature for ages, but it's never been really implemented in first principle calculations. It's very simple. If we consider the current from this atom to the next atom, we just need to know the velocity operator. The velocity operator is a commutator of position operator and Hamiltonian. And then, in the end, we just need to calculate the expectation value of this velocity operator. Then we get the charge current. And here is nothing but the hopping Hamiltonian. It makes sense, right? So the current is just given by the hopping of electrons. And this is the charge current along a certain direction. And if we want to study the spin current, we just replace this velocity operator by spin current operator. And then we get the spin current from this atom to the next atom. And this average just makes this spin current operator Hermitian. So having this one, we are able to study, for example, for the bulk spin Hall effect in bulk material, or we can also make a real interface between ferromagnetic material and normal metal and study the spin Hall effect and the inverse spin Hall effect. here. And as I said, we need a model a realistic interface, because, for example, permalloy and platinum has a very large lattice mismatch. And in order to do it, we choose 3 by 3 permalloy unicell to match root 7 by root 7 platinum. Then we reduce the strain within 1% of the lattice. So this gives us some real effect, because we don't want to stretch the permalloy to be like platinum or the other way around. That I see that it will become completely another material. So let's look at the spin Hall effect in pure platinum first. So here we know if we have electron flowing along this direction, it will generate spin current along this direction and this direction. And we just take a cross section of this area and also the other area. We check the spin Hall current density, and they are quite equal within the numerical accuracy. The error bar gives the measure of different random configuration due to populating phonon. So this is also temperature, room temperature calculation. And they are quite consistent with each other. And in order to extract the spin Hall angle, we just integrate from the interface to a certain length. Then we get a linear dependence, and from the slope we get the spin Hall angle is 3.3% for platinum at room temperature, and error bar is pretty small. Okay, so this is the room temperature value, and we can also vary the temperature to see the spin Hall angle, how spin Hall angle depends on the temperature. We see it's basically linear, and here there's a slight curvature. It reminds us the temperature-dependent resistivity, right? You have basically linear dependence at high temperature because of the bi, and also the low temperature you have block T23, T25 relation. And we can also plot the spin Hall angle as a function of resistivity in a log-log plot, and we see the perfect linear dependence of the spin Hall angle on the resistivity. That is what? The spin Hall angle proportional to the resistivity, then the spin Hall conductivity is a constant. Here I got about 3.2 times power 5 ohm meter, inverse ohm meter. And this value is agreed with Professor Bohr's calculation, 4.4. And up to here, I should mention that the largest, the giant spin Hall angle for materials was discovered in some crazy material, beta tantalum or beta tungsten. Both of them have very high resistivity. So it might be related to this kind of a correlation. And then that's just bulk value. That doesn't tell us anything. So then we started the interface. Let's look at what interface plays a role in spin Hall and inverse spin Hall. Actually, we can calculate simultaneously the spin Hall and inverse spin Hall in this structure. Because, of course, there's when you drive a current, there's a spin Hall automatically. And at the same time, the current injected into platinum is spin polarized by ferromagnet. So there will be a spin current injected into platinum. And according to inverse spin Hall, there will be transverse charge current. You can measure it. So for the spin Hall effect, we got a similar picture as the previous for bulk value. Here is 0.3, but the most shocking result is that the interface, it gives you giant contribution, so more larger than 20%, right? So then we just put here. So it gives us suggestion that the interface is quite different from bulk. And then we look at the inverse spin Hall effect. As I said, when the charge current injected into platinum, it is polarized, and the spin polarization of this charge current follow this spin diffusion equation, Valley-Furter equation, and this is a log plot. So it's perfect exponential, and the value is 5.6 in agreement with previous Bauer calculation. And you see at the interface there's a little bit stronger, quicker decrease. That corresponds to the spin memory loss. So all the pictures are consistent. Now, if we look at the inverse spin Hall effects, we can multiply the spin current by a bulk spin Hall angle. Then we have this orange line here. It agrees with the calculated values dots in bulk region, but not at the interface. Again, it suggests us that we need to take interface in different way. So let's look at what we really see in this inverse spin Hall effect. When we measure the inverse spin Hall voltage or current, we include both the interface contribution and the bulk contribution. And if we consider the effective spin Hall angle by the total charge current divided by total spin current, we end up with this curve, effective spin Hall angle as a function of thickness of platinum. And you see it never approaches the bulk value, but saturates at a much larger value here. And if we want to model the interface by an effective interface spin Hall angle and the bulk angle, we know we already calculated, and the spin diffusion length we already calculated. We can find we can get an expression with two parameters. One is interface spin Hall angle. One is this spin current ratio. All the other parameters we know by independent calculation. So we can fit this curve nicely by this expression, and this gives us the interface spin Hall angle is about 25 times larger than the bulk value. So this is the sort of the conclusion from our calculation for spin Hall effect, and that tells us that we really have to take into account the interface contribution in the interpretation of experimental observation. And how can we exploit this large interface spin Hall angle? Well, the simplest way is to use highly resistive platinum, for instance. First of all, platinum with larger resistivity give you larger spin Hall angle, bulk angle. And also, when the platinum is highly resistive, it will push the current density onto the interface. So then you have large contribution of the interface spin current. This is another way to improve the efficiency of magnetization switching. So since the time is almost over, I want to give you some conclusion that I hope I have convinced you that the interface plays a very important role in spin transport, spintronics, that has been overlooked. And we really have to take into account properly in the spin pumping and also the spin Hall effect. So, thank you for your attention.
Thank you very much. Yeah?
According to your picture, so if platinum is bulk, there's no conduction. If everything current flows only on the interface, then that will be the best